Good morning. Today we'll speak about structural equation modeling, abbreviated SEM. SEM in Swedish, strukturekvationsmodellering. And I put together content like this. So we have a look at what kind of data do you have? What kind of data is suitable for structural equation modeling? And then some phrases here: latent and manifest variables, exogenous and endogenous variables. So some phrases here. Different type of SEM models: path model, confirmatory factor analysis, and full model, if we call it like that. How we specify our model. One of the main results, parameter values. What do they stand for? The other main result is fit indexes, how well the model fits data. And I'll finish here with talking a bit about model modification. So that's the content here. Difference, similarity with ordinary regression analysis, because it's a kind of regression analysis. Well, all statistics are actually. All statistics are regression analysis, only different variations of it. SEM is often more confirmatory. So you have some kind of hypothesis, you have some kind of theory, and from these hypotheses, this theory, you translate to a model. And then you fit the model to the data, and you see how well it fits with the data. While in regression analysis, it's more usual to try various solutions. You have a lot of predictors. You look at their effect on the various outcome variables. With SEM, it's more easy to get lost. So it's more crucial to have some kind of hypothesis you're testing. You can't test everything with it. In SEM, we adjust for measurement error. We don't, while in regression analysis, we assume we have perfect reliability in the measurement of our variables. Of course, we know we don't have perfect reliability. But mathematically, the analysis assumes we have perfect reliability in the measurement of our variables. While in SEM, we take the reliability of the measurement into consideration and can adjust for this when we calculate our parameter values. What this usually leads to that the parameter values are stronger. We get stronger effects, we get stronger correlations when we conduct SEM compared with ordinary regression. So SEM usually have higher power than ordinary regression has. Similarity here. Ordinary regression analysis as well as SEM is usually used with non-experimental data. Of course, you can use them with experimental data also. But quite often you have a number of continuous variables. Some of them you treat as indicators of some latent variable, and you have a look at association between latent variables. So that's a similarity. What kind of analyses go hand in hand with experimental designs when we conduct experiments? ANOVA is quite usually used with experimental data, because then you divide individuals into a few groups, and you do something with one group, and you use some other group as control group. So you have one or a few experimental groups, control group. You do something with them, and you measure your outcome variable, and you might do this on various occasions, and then you conduct a mixed ANOVA on the data. So ANOVA and experimental design usually go hand in hand. Regression analysis, structural equation modeling, quite often used with non-experimental data. But you can use it with experimental data also. So data could look like this, for instance. So I have simulated data from one study here, von Sturm et al. From the journal Intelligence. Okay, so we have various continuous variables here. We have 4 measures of intelligence here. 4 intelligence tests. Verbal 1, verbal 2, arithmetic, and English test. So the values there stand for the result on those intelligence tests. Level of education, and so on. Family housing tenure. Well, actually, some of these were not continuous in the original study, but I have simulated the data, so they become continuous here. So continuous variables. Sometimes you might have dichotomous variables also. So the same kind of data we use in regression analysis. And from this you build a model. So von Sturm et al. In their study, they had a model like this. So the boxes here, they're called manifest variables. That's the variables we have in our data set. On those variables, the subjects actually have values. So here, for instance, here are our intelligence tests. On those, people have values. We have some variables here, and so on. Level of education, manifest variable, people, manifest observed variable. People actually have values on those. Okay, what this model states here is that we have a non-observed latent variable here called G, general intelligence. So people don't have values on that in our data set, but we assume it exists. There is a variable, a latent variable, general intelligence, that affects what result, what values our subjects have on those 4 actual intelligence tests. So a single-headed arrow here means has an effect on. So this states that general intelligence has an effect on the results on those 4 intelligence tests. So latent variable, non-observed variable, can also be called a factor. Here we have another latent variable, factor, social class of origin. We assume it's not observed, but we assume there is something called social class of origin. And people vary. Some individuals have higher values on that, others lower. And whatever value subjects have on that social class of origin will affect what values they have on these latent, on these manifest variables, on these manifest indicators. Housing tenure, father's occupational status, mother's occupational status, and so on. So manifest indicators, they indicate what value people have on the latent variable lurking behind the scenes here. So single-headed arrow causes, has an effect on. There is a regression effect from this on that. So here, for instance, we say that general intelligence has an effect on level of education. Level of education has an effect on social class of destination. That's the one we have here. What social class these subjects have later on in life, about age 40. Double-headed arrow correlates. So here we say that general intelligence, the latent variable, and the latent variable social class of origin, they correlate with each other. We don't say that one of them has an effect on the other one. We say here there is a correlation. General intelligence, and this B here is behavioral disturbance. We say they have a correlation. Social class of origin, behavioral disturbance, also has a correlation. Yes?
But the names that are given to this latent variable are something that we implement.
Yes.
Like the factor analysis.
Yes. It's the same way as in factor analysis. We decide What are those variables indicators of? No, we do it. We said, this is our model. Please test how well it fits with data. Calculate the parameter values and tell me how well the model fits data. But we have to draw the model.
You decide yourself which is correlation, which one correlates, which one is effect.
Yes.
You decide.
We decide. Where do we have a correlation? Where do we have a regression effect? We decide that. So that's latent and manifest variables. Latent, non-observed factors, manifest variables, manifest indicators, actually observed variables that people have values. Exogenous and endogenous variables, nice words. They look nice when you write a paper. Yes, I did that not too long ago, and one of the reviewers did not know what they meant. That also always feels nice when you can give a small lecture to the reviewer. Exogenous, well, they are simple words. Exogenous is the same as independent variable. Something that has an effect on something else. And endogenous, dependent variable. Something that is affected by something else. And some variables can be both exogenous and endogenous, both dependent and independent in the same model. So for instance, education is our spider in the web here in this model. Level of education is endogenous, is dependent in relation to general intelligence, social class of origin, and behavioral disturbance. Because it's affected by those. It has no effect on them, but they have an effect on level of education. However, education is exogenous in relation to social class of destination. What social class you will have when you are about 40 years old. Because it has an effect on social class of destination, rather than the other way. So some variables are both exogenous and endogenous. Some are only endogenous. Usually the manifest indicators we have, they are only dependent. They are only endogenous. They are affected by their latent variable, but they don't have any effect on something else. We have three here that are only independent, only exogenous, namely general intelligence, social class of origin, and behavioral disturbance, because nothing has an effect on them. They correlate with each other, but that is not enough for a variable to be endogenous. I think I wrote exogenous there in the handout, but it should say endogenous there. A correlation is not enough for a variable to be treated as a dependent variable. So those three are only independent in this model. There are different kind of structural equation models. I guess we could group them into four main categories here. We have path model. Maybe somebody would say it's not really a structural equation model, but path model, we have only manifest variables, no latent variables. So in this case, we have a data set. People have values on all four of those variables, and we build a model. We say that the values on the variables relate to each other in accordance with this model. So we have reading. I didn't even read that, but I guess we have reading ability, writing ability, which they correlate with each other, have an effect on math ability, and then all three of them has an effect on, I don't know, science ability, scientific ability. So people have values on those four, no latent variables. confirmatory factor analysis, CFA, we have latent variables. So we have a number of manifest indicators, and we have a number of latent variables. So in this case, we say that those manifest indicators, manifest variables, are indicators of that factor. Those three are indicators of that factor, and so on. So it's the same as factor analysis. We allow the factors, the latent variables, to correlate with each other, but they have no effect on each other. They only correlate with each other. That's the normal way to specify a confirmatory factor analysis. There's one anomaly in this figure, though. There's one extra effect here. From that factor onto that manifest indicator. So we say that this indicator here, this manifest indicator, loads both on that factor and that factor. I guess that was not expected from the beginning, but they saw in the data that the fit of the model became better if they let that item load on both factors. Things like that happen. And then the grand finale here, a full model. We have latent variables, and some of them are independent and some of them are dependent in relation to each other. A few things to think about when you specify your model. So I made it a bit simpler here. I took away the behavior disturbance factor. So we have social class of origin. What social class these subjects have in their childhood, based on a few factors here. Mother's occupational status, father's occupational status, number of rooms in the housing they're living in, family housing tenure. It's if they own their own housing or if they're renting. It's British study. That's a big thing in Britain. Only poor people rent their house. I don't know if it's true, but it's seen as an indicator of class, whether you rent your house or not. Okay, so those are seen as indicators of social class of origin. Those four are seen as indicators of general intelligence. We have level of education later on when these subjects are in their teens, and then social class of destination when they're about 40 years old. Own housing tenure, number of cars they have owned by age 40, income, there's something more there I can't see, occupational status also. So, and we specify that those factors associate with each other in accordance with this model. Each endogenous, each dependent variable should have an error term. There are exceptions to this rule, but that's the normal. We give each dependent variable an error term. So here, for instance, we assume there is general intelligence and that it varies among these subjects. And whatever general intelligence the subjects have will affect their result, their result on that intelligence test, verbal one. So we assume there's an effect. But we don't assume that there's 100% explained variance. We don't assume that general intelligence explains 100% of the variance in that intelligence test. So we assume there's some kind of error here. Error variance, having an effect on the result here also. If we did not have that error term, so that's an error term for that dependent variable. If we did not have it, what we specify in this model that we have 100% explained variance here. And usually that's not a wise assumption, because we seldom expect to have 100% explained variance. The same with the rest. So all indicators here have an error term. Level of education, we say that social class of origin and general intelligence have an effect on level of education later on in life, but we don't expect 100% explained variance, so we have an error term here also. Non-explained variance and social class of destination. Non-explained variance. According to this model, what social class of destination you will have is affected by those variables, but we don't expect 100% variance. We have non-explained variance also. So error terms. So the only variables here that don't have any error term are those that are only exogenous, only independent, namely general intelligence and social class of origin, because they're not dependent in relation to anything else. So we're not explaining variance in them. So they don't have any error term. Another thing when we specify a model. You see here, we have, it says 1 there. 1, 1, 1, and so on. Each latent variable, this is the usual way to do it. Each latent variable are given one, so to speak, one factor loading that is specified to 1. It's specified to be 1. So here we say that the effect from general intelligence, the non-standardized effect from general intelligence on that test verbal 2, the non-standardized regression effect equals 1. Social class of destination, the latent variable, have a non-standardized regression effect on number of cores that is specified as 1. Why do we do this? Well, for instance, we want to calculate the effect of general intelligence on social class of destination. We want to calculate that regression effect there. What do we need to know? What information do we need? What values do we need in order to be able to calculate that effect? Well, we have to know the variance in social class of destination. We have to know the variance in general intelligence. Because you can't calculate the effect of one variable on another one without knowledge of the variance in those variables. However, both of them, general intelligence and social class of destination, are non-observed variables. We don't have them in our dataset, so they don't exist. And because they don't exist, they don't have any variance. So we have to ascribe variance to them. And one way to do this is to say that their effect on one of their manifest indicators, we specify it as 1. Because now, verbal 2 here is an observed variable. So we can calculate the variance in that variable. So we know the variance here, and we specify that effect equals 1. From this information, it can ascribe the latent variable general intelligence variance. Okay, in that case, the variance of general intelligence is. So it calculates. Given this, what is the variance in general intelligence? Given this, what is the variance in social class of destination? So now we have ascribed them variance, and therefore we can calculate what effect we have from that latent variable on this latent variable. So every latent variable has one outgoing effect that is specified as 1. And this is true also for the error terms. And now you might wonder, does it matter? Because for general intelligence here, for instance, we have 4 outgoing effects to choose among. Which one do we choose to specify as 1? Well, actually, it doesn't matter. Because we will mainly be interested in the results we present or the standardized effects. And when we calculate the standardized effects, it's not affected by variance. Beta weights are not affected by the measurement unit, so to speak. So it's not affected by what variance the variables have. Okay. So the standardized effects will be exactly the same, whatever of these effects, these factor loadings we specify as one. It's not affected by this. The thing we miss is we won't get a p-value for those effects. That's what we miss. But usually the effects from a latent variable on one of its manifest indicators, usually they are strong and highly significant. If you absolutely want to see the p-value for that effect, well, you can conduct the same model, but you choose to put somebody else, some of the other effects as one. And then you get the p-value for that also. So we say that if social class of destination increases by one step on its measurement unit, then number of cores increases by one on its measurement unit. One means that there is a positive effect. 0 in regression terms. You might be thinking about odds ratios, risk ratios. Then 1 is no effect. But in regression, 1 is an effect, a positive effect. So those two things we have to. Each dependent variable gets an error term. Each latent variable gets one outgoing effect, one factor loading, so to speak, that we specify as 1. Structural equation models, full models, are said to contain two different parts. Measurement part. The measurement part is the association between latent variables and their manifest indicators. So here's 1, 1, and 1. And we receive those effects. So in the measurement part, we have the effects from latent variables on their manifest indicators. What are those effects? The same as something we came across last week. How do we interpret these effects? How do we interpret those effects? Yeah, the same thing as factor loadings. So the measurement part contain factor loadings. And then we have the association between the latent variables. And in this case, we also have education here in that part. The structural models, the structural part of the SEM model. And here, of course, those effects are the same as regression effects. They are the same as effects in multiple regression. Okay, let's be a bit philosophical here. So we have two variations of measurement model here. So in this we state that we have general intelligence here, a G factor, and it has an effect on those 4 manifest indicators. The effect runs in this direction. And here we have something similar but completely different. You say we have a G factor here, general intelligence, and it's affected by those manifest indicators. This on the left could be called a reflective model, and this one on the right could be called the operational model. What do we say here? If we specify our measurement model in this way, what do we say? What do we assume? We don't think about this when we conduct the damn analysis, but actually what we assume here is we assume that there is something as general intelligence. It exists. We are stating a scientifically realistic view. Scientific realism is that you assume those things you talk about, they actually exist. So if we talk about quarks, we assume those exist. We assume that black holes exist. We assume there exists something called health. Although nobody has ever observed health, we still assume it exists, and so on. That's scientific realism. And in this case, general intelligence. Nobody has ever observed general intelligence. It has no color. It can't be observed. But we assume it exists. And people walk around carrying their general intelligence with them. And it varies between individuals. And now they sit down and fill in a few tests. And we assume they take their general intelligence with them, and whatever general intelligence they're carrying around will affect what scores they will receive on those 4 tests. So we assume the effect goes from general intelligence on to those manifest indicators. So, what do we not assume? Well, assume one of the subjects here drops his pen or something, his or her pen while doing the test, and runs out of time. So, receives a worse score on verbal 1 here than he or she would otherwise get. What changes according to this model? Is there a change in this person's general intelligence? If due to a random factor he or she receives a worse score on one of the tests than he or she would actually get otherwise? No, because we state that there is no effect from this test on general intelligence. The effect goes in the other direction. So if a person would lose his or her pen, what happens is that the error term here increases. We have more of measurement error than we otherwise would have. But there happens nothing with the person's value on this latent variable. This, on the right, operational model. What does it say? Well, it says that general intelligence is nothing beyond the values on those manifest indicators. So the only thing we mean by general intelligence is a summary of person's results on those four tests. So if a person would lose their pen there, well, then it has an effect on general intelligence, because general intelligence is nothing beyond the results on those tests. And of course, this has some history, which you would choose in psychology, my area. These are the behaviorists. They don't like things that they can't observe. So if they use some phrase, they only use it in order to describe something that is possible to observe. So if they would ever use a term like general intelligence, the only thing they mean, it's a summary of actually observed values. It has no existence beyond that. While most people, probably without much thinking about it, assume this. We assume there is something. We can't observe it directly, but it exists. We can observe it indirectly by its manifest indicators. This is much more usual, the reflective model, than the operational model. But Skinner would never do. If Skinner would ever conduct a structural equation modeling, he would not choose the reflective model here. I don't know. Do you have any preference? Do you feel any preference for one of these? Well, you can do both. You can choose. However, if you choose the one on the right, you have to argue more, because it's not the norm. The one on the left here is the norm. Identification. In order to get a solution, in order to calculate parameter values and get the result, your model has to be identified, as it's called. Which means that you have enough information in your data set in order to come up with a unique solution for your model. Unique solution with unique parameter values. And for a model, the amount of information in your data set that you are going to use in order to calculate your model equals the number of variances and covariances in the data set. And the number of bits of information, if we use that phrase, it can be calculated by this formula. So number of variables, number of manifest variables that are going into the model multiplied by number of manifest variables plus 1 divided by 2. Okay, so if we take an example here. So assume we have 4 manifest variables in our model. That would give us 4 times 5 divided by 2. 10 bits of information here. So those 10 we are going to use in order to calculate our model. We have 4 variances, 1 for each variable, and 6 covariances. And covariance is the same thing as non-standardized correlation. So we have this amount of information that we are going to use to calculate our model. So in our model, we won't be able to calculate more than 10 parameters. We can't calculate 11 parameters using 10 values, 10 bits of information. If I make a comparison, imagine we're going to calculate 2 parameters, x and y. And we have the information that x plus y equals 5. How many bits of information do we have here? We have 1 bit of information. We know that the sum of x and y is 5. That's 1 bit of information. How many parameters are we going to calculate? 2. Can we calculate 2 parameters from 1 bit of information? Can we get a unique solution for x and y here? What is x and what is y? Well, it could be a lot of things. 3 and 2, 1 and 4, 4 and 1, minus 2 and 7, and so on. So there's a infinite number of combinations that will give this. However, imagine we also know that x minus y equals 1. Now we have 2 bits of information and we're going to calculate 2 parameters. Can we calculate a unique solution from this? Yes. From this we know that x must be 3 and y is 2. Can't be anything else. If we also, so in this case we would say that our model is just identified. We have the same amount of information as parameters we are going to calculate. Usually we might have even more information. We might also know that, 3x equals 9 and so on. Then we have even more information. We have 3 bits of information, but we only going to calculate 2 parameters. Our model is over-identified, as it's called. So our model has to be identified in order for us to be able to calculate a unique solution. So the data set has to contain at least as much information, bits of information, as number of parameters we are going to calculate in our model. So number of parameters we are going to calculate, or the sum of non-specified regression effects, number of correlations, and number of exogenous latent variables, because we have to calculate the variance for those. So what we get is a degree of freedom for our model, which is the difference between number of bits of information in our data set and number of parameters that are going to get calculated. So if you take amount of information in the data set minus number of parameters, we get degrees of freedom for our model. If we have a positive value on that, our model is said to be over-identified. We have more information that we need in order to calculate our parameters. If it's negative, it's under-identified. We can't calculate our model. We can't calculate a unique solution. If number of parameters and number of bits of information are equal, so we have 0 degrees of freedom, the model is said to be just identified. We can calculate a unique solution, but there are some other things we can't calculate. We don't get model fit, for instance, in this case. How well the model fits to the data. We get the parameter values, but we don't get the model fit. Because degrees of freedom are usually involved in the calculation of model fit. So you might, for instance, multiply by degrees of freedom. But if degrees of freedom is 0, well, then the model fit becomes 0. The specific measurement of model fit might become 0. Or you divide by degrees of freedom or something like that. Okay, so we want our model to be over-identified. We want it to have as many degrees of freedom as possible. So if you take our example here, how many bits of information do we have in our data set? Well, if I calculate here, if I count, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 manifest variables. So 14 times 15 divided by 2, we have 105 pieces of information, so to speak, bits of information in our dataset. 14 variances and 91 covariances. How many parameters do we calculate in this model? Well, we have 15 non-specified regression effects. So all the regression effects, except those that we have specified to 1. So there are 15 of those. We have 1 correlation. We have 17 exogenous latent variables. All the error terms. So 4, 9, 13, okay, 14, 15, and also social class of origin, 16, and general intelligence, 17. We have to calculate the variance for those. So 17 exogenous latent variables. So 15 plus 1 plus 17, we have 33 parameters to calculate in this model. So, and we have 105 pieces of information. So degrees of freedom for this model, 105 minus 33, 72 degrees of freedom. We have 72 pieces of information more than we are going to calculate parameters in this model. So it's over-identified. We get the solution. So we came to parameter, maybe the main result, together with the model fit. So how do we interpret the values we get here? Well, in the same way as we have done previously. So here, for instance, we calculate that there is a correlation between general intelligence and social class of origin of plus 0.44. So quite strong positive correlation. The higher the social class of origin, the higher the general intelligence. However, in this case, the correlation has been calculated while adjusting for non-perfect reliability in the measurement of general intelligence and social class of origin. Differently, if we would have two index variables here instead, one for general intelligence and one for social class of origin, we would not know with what reliability have they been measured. So when we calculate correlation, it's assuming, so to speak, that we have perfect reliability. But here, because those two are latent variables with manifest indicators, the program can calculate what is the reliability in the measurement of general intelligence. What is the reliability in the measurement of social class of origin? And then it adjusts for those non-perfect reliabilities, because the reliability is never perfect. So actually the correlation here is, this is how strong the correlation is between general intelligence and social class of origin when adjusting for non-perfect reliability. This is how strong it would be if we had perfect reliability. And the adjustment usually increases the value. So the correlation here is stronger than we would get otherwise with index variables, which I'll show soon. We get regression coefficients here. So here, for instance, 0.14, the effect of general intelligence measured at 11 years age on social class of destination measured at about 40 years of age. So 0.14, and this is the standardized coefficient. So how do we interpret that? Well, in the same way as a regression coefficient in multiple regression. If general intelligence increases by 1 standard deviation, what do we expect will happen with social class of destination? Increase by 0.14 standard deviations, given that what other factors? What other factors? To be specific, well, other factors that also has an effect on social class of destination. In this case, education and social class of origin. If we keep education and social class of origin constant, an increase in general intelligence by 1 standard deviation is expected to be associated with an increase in social class of destination by 0.14 standard deviations. If we keep general intelligence and social class of origin constant, an increase in educational level by 1 standard deviation is associated with an increase in social class of destination by 0.41 standard deviations. So those are interpreted the same way as standardized regression coefficients in multiple regression analysis. The effects between latent variables and their manifest indicators interpreted the same way as factor loadings. So do we have some rule of thumb here? When do we think they're okay? When do we think factor loading is okay? Well, 0.4 is one indicator, but usually they're stronger. We want them strong. We want them high. And usually, I don't know if it makes things difficult, because I have actually never tried it. If you have indicators that measure the same factor but in opposite direction, we mirror it, we reverse it before we put them into the model. So usually we have only positive factor loadings here, no negative loadings. However, of course, in the original data there might be some reversed item, but we reverse them first before we put them into the model. So only positive factor loadings here. Okay, we also get squared multiple correlation, R square. It's difficult to see in the model here, but there it says 0.33 for education. What does it mean? Well, it means that 33% of the variation in education can be explained by what? Yes, and those are intelligence and social class of origin. Intelligence and social class of origin together can explain 33% of the variance in education. You can't see it here, but I think it was 29. Intelligence, education, and social class of origin together explain 29% of the variance in social class of destination. So R square we get, and we get one for each. Those stand for R squares also. We don't get any R square for general intelligence and social class of origin. Why not? Well, social class of destination is also latent, but we still get the R square here. They're only independent. We're not explaining variance in them. They're only exogenous. They're only independent. So they're not dependent in relation to some other variable. So we're not explaining variance in them. So this is how we interpret the parameter values. And in the output, you can get a p-value for them also, except for those we have specified as 1. So here, for instance, social class of origin on family housing tenure, it has been specified as 1. We don't get the p-value for that. General intelligence on the English test specified as 1. We don't get the p-value for that. For the others, we receive a p-value. And now the thing is, when we specify our model, by drawing an arrow, by drawing an effect, we say there is an effect. There is an effect or there is a correlation. So what we expect is only significant values here. So in this case, we have one that is not significant. Social class of origin has no significant effect on social class of destination. That effect is not significant. So, of course, you don't always do this, but it makes you wonder, maybe you should delete that effect from the model, because it's not significant. So, what do we gain by deleting a non-significant effect? It might improve the fit, we're not sure, but we gain 1 degree of freedom. So the model becomes more simpler. And everything else equal, we want a simple model as possible. We usually don't retain effects that are not significant. Of course, if they're not too far from significance, we might retain them. But quite often we delete them. In a structural equation model, we can have 3 different kinds of effects. We don't always have all of them, but in this case we have all of them. We can talk about direct effects, indirect effects, and total effect. Direct effect, that is the values we have in those are the parameter values we have in the model. So direct effect is the effect of one independent variable on a dependent variable while keeping other variables that have an effect on the same dependent variable constant. So regression coefficients in a multiple regression. So, of course, these are the direct effects. Indirect effect is the effect an independent variable has on a dependent variable via some other variable. It's also called mediated effect. Indirect effect and mediated effect is the same thing. In this model, we have two mediated effects. General intelligence has a direct effect on social class of destination, but it also has an indirect mediated effect, namely via education, because intelligence affects education and education affects social class of destination. And the other indirect effect is social class of origin via education on social class of destination. So according to this model, level of education to some degree mediates the effect intelligence and social class of origin has on social class of destination. It mediates partly those effects. If we did not have this effect, or according to the slide before, this effect was not significant. Okay, so we might delete it. Would that mean that social class of origin has no effect on social class of destination? No, social class of origin would still have an effect on social class of destination, but it would be fully mediated via level of education, because it has an effect on education, and education has an effect on social class of destination. Now, when we have both direct effects and indirect effects, we say that education partly mediates the effect of intelligence and social class of origin on social class of destination. How are those indirect effects calculated? Well, it's the product of the two effects. So here, for instance, general intelligence, if it increases by 1 standard deviation, level of education increases by 0.48 standard deviations. Okay. If education would increase by 1 standard deviation, social class of destination would have increased by 0.41 standard deviation. But now it only increases 0.48 standard deviation. So 0.48 multiplied by 0.41, 0.2. So if intelligence increases by 1 standard deviation, we expect social class of destination to increase 0.14 standard deviation, but a further 0.2 standard deviation via the effect intelligence has on education. If social class of origin increases by 1 standard deviation, we expect social class of destination to increase 0.06 standard deviation, but also a further 0.07 standard deviation, because an increase in social class of origin leads to an increase in education, and an increase in education leads to an increase in social class of destination. Okay? So an indirect effect is the product of the two effects. The effect of the independent variable on the mediator multiplied by the effect of the mediator on the dependent variable. That's how you get your indirect effect, the size of it. Correlations are not involved in indirect effects, because according to this model, we have defined that as a correlation. So if social class of origin increases, we don't expect anything to happen with G.
Because it's not causal.
It's not a causal effect. It's, so to speak, only a correlation. So correlations are not involved. If we had defined that, not as a correlation, but a causal effect, then there would be a lot of indirect effects. Then social class of origin would have an indirect via education. It would have an indirect effect via G and social class of destination, but it would also have an indirect effect via general intelligence, via education on social class of destination. So in that case, there will be multiple ways of social class of origin to affect social class of destination. So how strong the total indirect effects become, which means total effect, it depends on how you define those associations. As correlations are in what direction the effect goes. Okay, so then the total effect, it could be defined that the expected change in the dependent variable when the independent increases by 1 standard deviation, given that mediating factors are not kept constant. We allow them to vary. So if we allow the mediators to vary, what will happen with the value in the dependent variable if the independent increases by 1 standard deviation? And the total effect is the same as the sum of direct and indirect effects. So the total effect of social class of origin on class of destination, 0.30. If social class of origin increases by 1 standard deviation, and we don't keep education constant, then we expect social class of destination to increase by 0.13 standard deviations. If we let education vary and intelligence increases by 1 standard deviation, we expect social class of destination to increase by 0.34 standard deviations. Of course, this value 0.13, total effect of social class of origin, would be much higher if we have defined that correlation between social class of origin and intelligence, not as a correlation, but instead as a causal effect. Then this value would be much higher. Of course, if the effect here would be 0 from intelligence to education, then there would be no indirect effect. The reason why the total effect here is larger than the direct effect is because intelligence has an effect on education. So if intelligence increases, we expect education to increase. Because it increases, also class of destination increases. Social class of origin has no indirect effect on education, only a direct effect. The same with G. It has no indirect effect on education, only a direct effect. If we had defined that there is an effect of social class of origin on G, then social class of origin would have an indirect effect on education. Then we would multiply the size of that effect with the size of that effect. But in this case, we define it as a correlation. Sometimes you can see something has a positive direct effect on a dependent variable, but a negative mediated. And some might be close to 0. So the indirect and the direct effect are neutralizing each other. Yes, the sign of the effect is taken into consideration. Because if independent has a negative effect on a mediator and the mediator has a negative effect on the outcome, then you think that if the independent increases, the mediator decreases, and if the mediator decreases, then the dependent increases. So the indirect effect is positive. Yes, but we expect the factor loadings here to be positive. But the effects in the structural part of the model, they might be positive, they might be negative also. It would be nice to have some example of negative effect here. They can be both positive and negative. So, structural equation modeling. Why use this? Why not use some old school instead? So if we use factor analysis and we calculate the values, we collapse items to index variables instead, like we did last week. So we could do that. Here I have tried it. So I take those 4 variables, indicators of intelligence, and I collapse them. For each individual, I calculate a mean on those 4. After standardizing them so they are on the same scale. So each individual, each subject receive 1 value, their G score. I collapse those 5 indicators of social class of origin and replace it with 1 value, index variable. And the same for social class of destination. Okay, so now every individual has a value on those 4. And then I do this in 4 steps. I have to do it in 3 different steps. I calculate the correlation between social class of origin and intelligence. 0.35. Step 2, to get those effects. The effects on education. I do a regression analysis. I use education as the dependent variable and intelligence and social class of origin as the predictors. I receive those effects, 0.5, 0.15, and I get the R square 32, 0.32. So 32% explained variance. And then in the 3rd step, I use those 3 as predictors and social class of destination as the outcome. And I receive those effects. 0.11, 36, and 5. 20% explained variance. We can compare those with the effects we have here. When we do not collapse items to index variables. Instead, keep them, the original data, and see them as indicators of latent variables instead. I guess the biggest difference here, the correlation here. Instead of 0.35, we get 0.44. Stronger correlation. Why? Well, it's because in the SEM analysis, it calculates the measurement error, the reliability in the measurement of G and social class of origin, adjusts for that, and we get a stronger correlation. Adjusting for non-perfect reliability, the correlation is calculated to be 0.44. Here it's because people only have 1 value on those. It doesn't know, the reliability doesn't come into the calculation. So mathematically speaking, we assume perfect reliability and calculate the correlation to 0.35. So generally speaking, the correlation, the effects here are slightly stronger. 0.41 there for education instead of 0.36. And so on. The only exception here became the effect from G on education. 0.48, 0.50, but.
So usually we do get higher values on C model.
Yes, stronger effects. More explained variance. Okay, not much difference. 33% here, 32. But here I have 20, here I have 29%. We get stronger effects, more explained variance in SEM model because it adjusts for the reliability. This is exactly what the same result as we would get in a path analysis. But then, of course, we would not have to do it in 3 separate steps. We just build a model and calculate it and get the parameter values. So usually it's recommended, if you can do structural equation modeling, don't collapse your observed variables to index variables. Keep them as they are. Keep the information. Consider all the information you can. It's better to do that than collapsing the items. The other main result we receive, besides parameter values, of fit indexes. How well the model fits the data. And we get values. We get quality scores. And it's exciting. You have a theory, you have a hypothesis, you build a model, you collect data, you test it, and then you sit there, now I'm going to calculate, you click. And you feel how your mood can be increased or decreased depending on what you see on your screen. So how does it do this? Well, of course, I can't tell everything, mainly because I don't know everything how it does this, but some words about it. What the program does is that it predicts correlations. We build our model, okay, and the program says something like this. Okay, that's your model. That's how you assume the variables are related to each other. If that is the case, I predict that the correlations between the manifest indicators look like this. So from our model, it predicts what should the correlations between the manifest indicators be, given our model. So predicted correlations, implied correlations, reproduced correlations. They can be called different things. Then, of course, we can, because we have the manifest indicators, we have, so to speak, the true correlations, the actually observed correlations. So now we can compare from our model predicted correlations between the manifest indicators with the actually observed correlations. How do we want those to relate to each other? The predicted correlations and the actual correlations. As close as possible. Because if they're close to each other, it indicates our model is good at predicting how the associations between the variables actually look like. We can calculate the differences between our predicted correlations and the actual correlations. What do we call that? The difference between predicted and actual residuals. Residual correlations. How much our predictions miss the actual values. And of course, we want these residuals to be as small as possible. So the smaller they are, the better our model is at predicting the correlations, the better our model fits to data, the better the model fits. And nobody expresses it like this, but if we are a bit philosophical. Our model represents our theory. So we have a theory, we have a hypothesis about how association between variables should look like. So the model represents our theory, our hypothesis, and the data represents the reality. So we're having a look at how good our theory fits with reality. If we get a good model fit, it indicates our theory is a good description of reality. Bad model fit, it's a bad description of reality. So let's say we have six observed variables. Those we have in our data set. And from those 6 we build the following model. We say that those 3 indicators of this latent variable. Those 3 are indicators of this latent variable. And there is an effect from this latent variable on that latent variable. Now, using maximum likelihood, the program calculates all the parameter values. So, given the data, this gives the best fit. Those have the highest likelihood of being the true values in the population that the sample is representing. So it maximizes likelihood. So we get these values. So now we could predict, for instance, given our parameter values here, how strong should the correlation between A1 and A2 be? Well, we can calculate it by multiplying that factor loading, 0.61, with that factor loading, 0.71. According to our model predicts that that correlation between A1 and A2 should be 0.43. And so on. We can predict how strong, in that case, if our model is the correct one, how strong should the correlation between A1 and A3 be, and so on. Now, of course, you might think, well, in that case, you only pick two values here that give exactly the actual correlation. But it's not possible. Of course, if you only have two indicators, then you can have factor loadings that multiply with each other, gives the exact correlation. But if you have more than two, then of course, if you change that one, you change this predicted correlation, but you also change the predicted correlation with A3. So there's a balance here. They probably don't give perfect predictions, but as good as is possible. And the same here in our data set, we have an actual correlation between A2 and B1, for instance. How strong does our model predict that correlation to be? Well, we can calculate that. 0.71 multiplied by 0.12 multiplied by 0.63. According to our model, the correlation between A2 and B1 is predicted to be 0.05. And so on. So we can calculate, according to our model, we can predict all the correlation between those 6 observed variables. And those correlations can be compared with the actual correlations between those six variables. And we want those predicted and observed correlations to be as equal as possible. So I picked the easy model here. I don't know how it's, of course, if you get complicated models with a lot of correlations and indirect effects and so on, it's more difficult to do this in a simple way as this. But this is how somehow it predicts the correlations. And we can get that as an output. So here, implied correlations. According to our model, after calculating the parameter values, and it calculates the parameter values so the residuals become as small as possible. So it doesn't get better than this. So these are the predicted correlations between the manifest variables, and these are the actual correlations. And if we compare, well, they're not perfect. The actual correlation between education and the result on this English test, 0.48. According to our model, it is predicted to be 0.49, and so on. So we have residuals. They are not perfect correlations, but we can note a few things. Education have observed correlation with the intelligence test that are strong, and they're predicted to be quite strong. Education has quite weak correlation with family housing tenure, number of rooms. It's weaker correlations here, and according to our model, they are predicted to be weaker. So although not perfect, it's not completely random either. There is some similarity between predicted and observed correlations. Occupational status, predicted correlations, actual correlations. The strongest actual correlation is with income. The strongest predicted correlation is with income. The weakest actual correlation, family car. The weakest predicted correlation, family car. So some relation, although not perfect, not completely random either. So from the difference between the predicted correlations and the actual correlations, it calculates fit values. How well does our model fit data? And it's from the difference between these it calculates. For instance, it can calculate a chi-square value from the difference between predicted and observed correlations. It calculates a chi-square value. And the larger the difference is, the larger the residuals, the higher the chi-square value. So we get a chi-square value for the model. How would we like that chi-square value to be? As small as possible. The smaller it is, the smaller the residuals. And we want small residuals. So in our example here, we get a chi-square value of 523. And our model has 72 degrees of freedom. From this, we can get the p-value. In the chi-square distribution, a value of 523 with 72 degrees of freedom is very significant. This means that we can't assume all residuals to be zero in the population. We can't assume that our model makes perfect predictions in the population. So how would we actually want that p-value to be? Non-significant would mean our model makes perfect, can be assumed to make perfect predictions. Or our predictions do not significantly differ from the actual values. If you're a real hardliner, then you say if the p-value, the chi-square is significant, your model is bad. But those are the those are the hardliners. That's Jöreskog and Sörbom in the 70s. Nobody says that like that. For one thing, the p-value takes into consideration the sample size. So given a certain amount of residual, the bigger the sample size, the lower the p-value gets. So if you want a non-significant p-value, have a small sample. It doesn't feel right to have it like that. So usually we don't put too much in focus on the p-value here. I never seen it to be anything else than highly significant with my data. I have a large data set, so I don't even care so much about it. One rule of thumb, more liberal, is that we take the ratio of chi-square and the degrees of freedom, and if that ratio is less than 2, it indicates good fit. But that's quite rough also. Again, considering that the chi-square is affected by sample size. Okay, fit indexes. So this is how the output looks in Amos. Not in other programs. So we get 3 lines in this output. Default model, that's our specified model. That's our model. Saturated model, it's a model where we have the same amount of parameters and as pieces of information in our dataset. So it has 0 degrees of freedom. So in this case, 105 parameters, 0 degrees of freedom. We could call it as good as it gets. I think that's why it presents this in there. I used to wonder, why does it present it? It's of no interest. I guess it wants to show what would be the optimal value, the perfect value that indicates perfect fit. So in this case, a chi-square value of 0 would indicate perfect fit. Independence model. Imagine we have a correlation matrix with zeros in every position. So the independence model assumes there's no association between the manifest variables. The correlations are all 0. So because we assume them to be 0, we don't calculate them. So in the independence model, we calculate only the variances of the variables. So in this case, because we have 14 variables, we calculate 14 parameters. So we could call that as bad as it gets. So of course, in this case, we have a huge chi-square value for that. So what some of these fit indexes does, they compare our model with this independence model. How much better does the model become when we add the parameters that we have added compared with the independence model with no associations between variables? So in this case, we've seen this already. Our model has 33 parameters, 72 degrees of freedom, chi-square of 523. The ratio between chi-square and degrees of freedom, 7.3. We get some other fit indexes. We get a lot of them. Okay. So here, for instance, root mean square residual, the mean residual. So imagine we have our residual correlation matrix, the means. This is affected by measurement units. So there aren't really any rule of thumb if it's good or bad. Of course, we want, because it's the mean residual, we want it to be as low as possible. Goodness of fit index. Imagine we take our actual variances and covariances as one column, and we take our predicted variances and covariances as one column, and then we do a regression analysis. So we predict the observed actual values from the predicted values, and we get the R square. It's the same as R square in a regression analysis. And of course, we want these to be as high as possible. It means that our predictions are good predictions. It can maximally be 1. According to some rules of thumb, a value above 0.95 indicates good fit, or at least above 0.9. There's an article by Hu and Bentler from 1991. It must have a huge number of citation, because they present in that article they present what they think are good criteria for these fit indexes. And for those indexes where 1 indicates perfect fit, they say that a value above 0.95 indicates good fit, close fit. Between 0.9 and 0.95, acceptable fit. So something like that. So above 0.95, we're happy. Above 0.9, we're content.
This is sort of like the R square.
Yes, it's actually exactly the R square. We predict the actual correlations, variances, covariances from our predicted. And we get the R square for that prediction. Adjusted goodness of fit index. It's based on goodness of fit index, but it considers degrees of freedom. So it rewards simple models. And when it comes to degrees of freedom, what is a simple model? It's a model with a lot of degrees of freedom. So given that the goodness of fit index would be exactly the same for two models, the adjusted would be higher for the one with more degrees of freedom. And so on. We have a lot of these. Those are quite popular. Normed fit index. I can show you in the previous slide here. We have a chi-square for the independence model. 7,683. And our model has a chi-square of 523. how large is the decrease in chi-square from the independence model to our model in percentage. That's what the normed fit index stands for. And of course, we want as low chi-square as possible, so we want the normed fit index to be as high as possible. And it can be maximally 1, because it can't decrease more than 100%. Hu and Bentler, it should be above 0.95, or at least above 0.9. And then we have other indexes here. They're all based on normed fit index. This is how it works. Somebody comes up with, how can we calculate model fit? Or we can do it by looking at how much the chi-square decreases when we add our parameters to the model. And people think, yeah, that's good. That's a good measure of fit. But then somebody thinks, yeah, it's good, but we should put some more emphasis on degrees of freedom. So they put degrees of freedom into the algorithm in order to reward simple models, for instance. And then we have some other slightly different. So in this case, incremental fit index. Okay. And others. Those are quite popular. Norm fit index, Tucker-Lewis index, comparative fit index. This one might be the most popular. I actually read a text that said this is the best one. Root mean square error of approximation. And here it's the opposite. The lower, the better. Hu and Bentler, well, good fit below 0.05. Acceptable below 0.08. Too high, not good. So we want it to be as low as possible. And then other ones. Okay, so we get a lot of output on this. So we have some rule of thumbs. I read this for Tucker-Lewis index, but I think the same applies to others that where one indicates exact fit. So something like this, with verbal labels on the different values. Below 0.85, unacceptable. 0.85 to 0.89, mediocre. Next, acceptable. Above 0.95, that's a good one. Close fit. Root mean square error of approximation. Those kind of labels can be used. Below 0.06, well actually 0.05, then you're even a bit more happier here. Close fit. In that range, 0.06 to 0.08 acceptable, and so on. Okay, I can show what von Stum did in the example I presented. This is from the results section. So we have 6,281 persons, subjects. The model has 96 degrees of freedom, chi-square 826 with a p-value. Okay, highly significant. Tucker-Lewis index, nice and high. Normed fit index, nice and high. Comparative fit index, yes, looks good. LMSEO, nice, low and nice. And then you say here, all path parameters were significant, except one here. Overall, the model had good fit to the data. And that conclusion, that description is based on these fit indexes. They all indicate good fit. Actually, very good, if you want to put in a very there. But mine had even better. So I did a similar analysis on Swedish data and sent it to the same journal, Intelligence. What?
Did you get it?
Yes. And because it was similar to von Sturm's here, I actually used exactly the same fit indexes here. I did it. She got hers published in Intelligence with this, so I took them exactly in the same order also. But I had like 0.99 was for my model. So that's an example. You get your own favorites. But I think RMSEO is almost always you present this one.
Why there are 23 way of
calculating the fit? Yes, but otherwise somebody statistical world dictator would have to decide, no, fit is calculated this way and no other way. There is no such. Yes, but you don't present all of them. You take a few of them, like here, and present them. Yes, I guess it's different in different areas. There it becomes different norms what indexes you use. In my area, those are pretty much. Always RMCO, norm fit index, comparative fit index. Those are the popular ones.
I have seen this AIC and BIC also in some papers on profile analysis.
Yes, they're quite popular. I have to admit, I know it's popular. Akaike information criterion. Mainly for comparisons. If you put in a new parameter, what happens? Because it's affected by sample size. So you can't give, a bit like with the chi-square, you can't say this is a good fit or it's a bad fit. It's more, if you have the same sample, you add a variable, you have a look at what happens with Akaike here.
And the one with lower index
is better. Yes. Last subject here, modification. I presented 3 different types of SEM models: path model, confirmatory factor analysis, and full model. But we could also maybe, the use of SEM could be maybe categorized in different categories. Different usuals of SEM analysis. First one is strictly confirmatory. You have a theory, you have a hypothesis. This you translate to a model. You have data, you fit the model to the data. And either you get bad fit, and you conclude, my theory, my hypothesis does not give good predictions. It has bad fit to reality. Or it has good fit, you say, my model is a good description of reality. My hypothesis seems to be a good hypothesis. So yes, no. Do you think that is usual to do it like this? Oh, it's quite risky. Imagine you get a bad fit and you present, no, it's bad fit, my hypothesis was bad. You send it to a paper, they send it back to you and say, no, thanks. So I guess number 2 is more usual. You have variations of the hypothesis. So you have the same research area, but there are slightly different hypotheses, slightly different theories. So you translate those theories to slightly different models. You fit them to data, and you see which one of them fits best to the data. And from this you draw the conclusion. This theory led to a model that fitted better to the data. Therefore, it's a better theory than the other one. So you let the theories compete with each other and see which fits better to the data. Quite popular to do it like this. Number 3 here, you might start with number 1. You have a theory, you have a hypothesis, and you fit it to data. You build a model, you fit it to data, you get bad fit, and then you start to think, how can I modify my model in order for it to fit better to data? So you conduct post hoc modifications of your model in order to improve its fit to data. How does it sound? Number 3 here. Does it have good reputation? No. It's nothing you brag about. Still, we do it quite a lot. Okay, some modifications you can do. You can check if your parameters are significant. If they're not, you might consider deleting them. The thing is, the chi-square of the model will always increase if you delete a parameter. So even a bad parameter will increase the predictive value of the model. So the chi-square will always increase, but then again you gain 1 degree of freedom by deleting a parameter. So what you can see is the increase in chi-square, is it significant if I delete this parameter? If it's not, you might delete it. You get a simpler model. And some of the fit indexes, well, quite a lot of them, take degrees of freedom into consideration. So they reward simpler models with more degrees of freedom. So some of the fit indexes might improve if you delete non-significant, weak parameters from your model. You might re-specify. So this is what you do when you have bad fit between your model and data. You might re-specify your model as a confirmatory factor analysis. If this confirmatory factor analysis has bad fit to data, it indicates there might be some problematic in your measurement parts of the model. Might indicate there might be some low factor loadings or so. You have low homogeneity, for instance, in some of the factors. Okay, so you could, for instance, calculate Cronbach's alpha for your factors. See if some of them could be improved by deleting some bad item. This should be indicated by weak factor loadings in the model, but might be not completely clear. Okay, so you work with your measurement part of the model in order to get that at least to have good fit. Sometimes, if you have problems in the measurement model, this happens quite a lot, I've seen. Okay, there might be some subgroups of your items. So you assume that you have, in this case, 6 manifest indicators of the same latent variable. So you have these in your model, but you get bad fit. And it might indicate that some of these factor loadings are quite weak. This could, for instance, be due to, you might have subgroupings of items. So it might be that those 3 manifest indicators, they are a subgroup, and those are another subgroup. They're indicators of latent variables on a different hierarchical level. And then you have your latent variable here on a higher hierarchical level. Classical in intelligence research, for instance. You have several intelligence tests, and they usually correlate quite highly with each other. But some of them correlate more strongly with each other than with others. And so people have concluded we have sub-types of intelligence. We have verbal intelligence, spatial intelligence, and so on. Different kinds. However, all of them are indicators of a more general intelligence. G factor. So sometimes if you spot there's some subgroupings, you re-specify your model like this, your measurement model, it improves the fit. You get better fit. Something else you can do is to have a look at your modification indices. Okay, and now we're fishing in murky waters here. So in Amos, other software also, you get something called modification indexes. So let's have a look at our model here. We fit this model to data. We get those values, fit indexes. RMSEO 0.076, NFE 0.93, and so on. How would we translate? What kind of verbal description would we give of the fit? Good, but could be even a little better. Quite good, acceptable. But we would like to have it a bit higher, a bit better. In Amos, we get these output, modification indexes. And what do they say? Well, here, for instance, E8 and E17. E8 is that error term there for the arithmetic test, and E17 is the error term for level of education. This one says if we let those correlate, E8 and E17, that covariance, unstandardized correlation, is predicted to be 1.7. And if we let those correlate, if we let them covary, this predicts that the model's chi-square value will decrease with at least 15.9. So it's a prediction of how much the model's chi-square value will decrease if we add these parameters. Decrease. Would we like the model's chi-square to decrease? Yes. The lower the chi-square, the better the fit. So how does it feel? Should we let E8 and E17 correlate with each other?
They are only on the latent error parts. I mean, they are only on this error estimation.
No, we can get others also. In this case, there's one between one error term, E14, and the social class of origin. So if we let that latent variable correlate with that error term, it would decrease, estimated decrease in chi-square 32.6.
Why don't we have such an interrelationship and changes between the recorded variables? Then it is more tangible to think if, for example, V8 and V2 are also intercorrelated.
Well, it's the same thing actually.
I mean, when the error measurements are...
Yeah, that the error terms correlate.
Oh,
it means that we have a correlation between those two items that cannot be explained by their correlation with with the same latent variable. So here, for instance, E5, E1. E5, E1. If we let those two correlate, it means that what that indicates is that those two, number of rooms and family housing tenure, those two have a stronger correlation with each other than predicted by them loading on the same latent variable. So if you have a positive residual on one of them, you tend to have a positive residual on the other one, and vice versa. It indicates they correlate more strongly with each other than predicted in our model. And actually, a correlation between the actual manifest indicators here, it would be a bit strange because we assume them to correlate, although we don't have the correlation here. We assume them to correlate because they both load on the same latent variable. So that correlation is, so to speak, already in there. But the correlation between the error terms indicates something slightly different. It seems like they correlate more strongly with each other. The residuals correlate with each other. The variance in those two that is not explained by the same latent variable correlate with each other. So, if you go back to this first one, does it seem like a good idea to let those two, E8 and E17, correlate with each other? What is the gain by letting them correlate with each other? The gain is decreased chi-square, a better fit. Right? What is the downside of letting them correlate with each other? We lose 1 degree of freedom. Okay. But chi-square value 15.9 with 1 degree of freedom is significant. Means that we get a significant improvement in the model's fit to data if we let those two correlate with each other. So only in statistical terms it would be a cost worth taking. Is there some other downside of letting those two correlate with each other? Yeah, the model, it's strange. How do we explain? Oh, you have a correlation there. Why? Well, I don't know, but I just put it there. E8 and E17, I felt like it. Is it in accordance with your hypothesis? Well, not really, but I put it there anyway. The model becomes strange. It's hard to motivate that correlation on some other terms except for model fit. So some of these are not as tasty as the others. It's stranger to let that correlation. See here, for instance, E14 and social class of origin. We let those two correlate with each other. How do we motivate that? It's strange. Okay, so some of them are easier to motivate than others, to justify than others. So, for instance here, E5, E1. They are both indicators of the same latent variable. Right? And they are both about living conditions, so to speak. Number of rooms and housing tenure. So it indicates that how you live is affected by your social class, but also by something else. It's not completely defined by your social class. So it feels like we can partly justify why we would let those correlate with each other. It seems like one of the most justifiable correlations between error terms here. And at the same time, it leads to a big decrease in the model's chi-square. So taken together, we might come to the conclusion, of course we might be criticized for this, but we might come to the conclusion, we let them correlate with each other. So we do it. We add a correlation there. Okay, as we see, we lose 1 degree of freedom. Chi-square decreases, actually by more than that 53, because it's some kind of minimum estimation. And the model fit here, it improves slightly. We are a bit happier. We would have, of course, wanted it to become even better, but it's a bit better. Of course, now we're fishing in murky waters here, because now we've gone beyond our hypotheses, our theories. Now we let the data decide our model rather than letting our theories, hypotheses decide our model. So it has no, it's like stepwise regression. It has not the best of reputations. We are data driven. Because of course, it might be something in our specific data set that makes this modification to lead to improvement in the fit of the model. In some other data set, it might look a bit different. So if you want to sort of keep your statistical honor, is there some way to do this? That seems more honorable than to just put it there, a correlation between error terms. Well, one way to do it is usually you predict, I have a hypothesis, I have a theory, I build a model from this. But quite often you can predict, it might not have the best of fits. So you assume from the beginning, I might want to modify my model, depending on what the data indicates. If you have a large data set, what you might do is that you take a sub-part of your data, not all of it, a part of it, and then you fit your model to the data, and you see how it fits, and might modify the model. But then you have saved the rest of the data for verification. So you do your fishing, you do your model modifications in one part of your data, and you save the rest for verification. It's like having two different data sets, two different samples. So instead of having one data set, you take your data set and you make two data sets of it.
It's only applicable on big data sets.
Yes, yes. But if you have 6,000, 3,000 is probably enough. Then maybe I did it like this in the article I was talking about. I had 49,000 people. I thought I will not get very good fit. I predicted that, so I saved half of the data, fitted my model to the other half. So are there some modifications I could make to improve the fit? I made the modifications. The fit was good. Then I tested the same modified model on the rest of the data, and the fit was good. So I wrote this in the paper. I did it like this, and of course one of the reviewers didn't. Why did you do it like that? Because my teacher have told me this is a good way to do it. Then of course you might still report the fit indexes for the full data. A warning. Can we draw conclusions about causal effects with the structural equation modeling? Here in our model we specify in what direction the effects run. So we say that intelligence affects education, not the other way around. Intelligence affects social class of destination, not the other way around. Of course, in this case, the variables have been measured at different ages. Social class of origin, when they're children, intelligence when they're 11 years old, education when they're in their teens or early 20s, and social class of destination when they're in the 40s. So of course, if there are effects, they should run in this direction rather than the other way around. But sometimes you have data that all measured at the same time, and you still specify that the effects run in certain directions rather than other directions. But of course, it's all based on correlations. So we can't be sure it's a real causal effect. As an example, this seems like a quite rational model, right? Let's make another model on the same data. We say that social class of destination in the 40s have a causal effect backwards in time to the level of education when they're in the 20s, and education and social class of destination have a causal effect even further back in time to affect what social class of origin these subjects will have, and what result they get on an intelligence test when they're 11 years old. Does it seem like a rational model? Causal effects backwards in time? No. But if you fit these two models to the data, what will we get?
Good model.
Yeah, they're exactly as good. Because the value of these are based on the correlation. We say it's a causal effect, but the actual parameter value is based on the correlation, the association between the variables. So of course, although we define them as causal or effect in one direction, we can't be sure only from this that it's a true causal effect. So again, when can we be more sure that a certain effect, certain association, is due to causality? Well, then we might need to have experimental data. We have manipulated the independent variable in order to see what effect it has on a dependent variable. Then we know that if there is an association, it's from the independent variable on the dependent variable rather than the other way around. If we administer a certain medication in differing amounts to a group of patients, and we decide what amount they will get, or we allow randomness to decide, and then later on we measure their health. If there is an association, we know it runs from level of medication on health rather than the other way around, because we have manipulated level of medication. It can't be affected by level of health. Okay. Yes?
So the only indication where we could compare some model and draw a conclusion is just by adding new parameters or deletion of new parameters into the model. And then to conclude, okay, so if this relationship is added to the model, there is an improvement or vice versa.
Well, of course, we might have more different models that not contain the same variables, and we still get the fit indexes, RMSEA, norm fit index, and so on for the different. And we can say, well, this model seems to have a better fit than the other one. But we can't make as cleanly the comparison.
So by just changing the direction of arrows between two specific variables
won't change the fit.
nothing will change.
No. It would be nice if it would be like that.
Disappointing at the end of the class.
You think so?
Well, now it's
No, it doesn't. The program doesn't know. It's only based on correlations. So it doesn't change by changing the direction of the arrow.
but because we're talking about endogenous and exogenous variables, then we might have it.
Yes, but mathematically there's still only two columns of values in the data set. If we know that one of them being measured in time before the other one, then of course, if there is an effect, it must be in this direction. It can't be, or at least we can exclude that it would run backwards in time. So we know this is wrong. We know this is wrong. Because that is measured when they're in the 40s and so on. But the program doesn't know. And if we have experimental manipulation, then we know we have it. Of course, one way to not get 100% certain conclusions about causality, but maybe more indications of causality if you have longitudinal data. So you can do structural equation modeling with longitudinal data also. So if we, in this example, we have measured a certain outcome variable at 4 different time points. So we have measured each subject 4 times. Okay, we can specify a model like this. This is called latent growth curve modeling. It's a subgroup of structural equation modeling for longitudinal data. So we say that what value people have in the outcome on those 4 time points, it's affected by an intercept and the slope. And the intercept stands for baseline value. What value you have in the dependent variable at the starting point, at the baseline. And the slope stands for the change in the outcome for each time unit. So let's say here we have measured the outcome at 4 times. Let's say, for instance, 1 month apart. So we say that the value in the outcome at baseline is the same as the intercept. There is no effect of slope on the baseline because the time has not started yet. So 0 is the value on time. The outcome value at the second measurement, well, the starting value is still the same. So the effect of intercept is always 1 on each measurement here. The intercept stands for the starting value, and of course the starting value is always the same. But now time has gone a month since the baseline. So the effect of the slope is 1 month. Third measurement point, intercept, still the effect is 1, but now the effect of slope is 2. Because now it has gone 2 months since baseline. And the last measurement is a combination of the intercept and the effect of 3 time units, 3 months. So in this case, we defined that these are the regression effects. But then you might wonder, if we define what are the regression effects, what is the result? What is the result we get? What is interesting with this? Well, what we let the program calculate is, for instance, well, the main result is we calculate a mean for the slope. A mean value. So we get the calculated mean for the slope with the standard error and a p-value. We have a look at that p-value. If it's significant, what does it mean? If the mean slope is significant, what does it mean? It differs significantly from 0. What does it mean if the slope, the mean slope, differs significantly from 0? What does that mean? There's a change in the outcome. The outcome value changes with time. And of course, the mean slope might be positive and significant. The value in the outcome increases with time. It could be negative and significant. The outcome value decreases with time. We have conducted another analysis that is pretty much equivalent to this before on this course. Which one? Oh, of course, it's not completely equivalent, but yeah, which one? Repeated ANOVA. Actually, this is better. Why is this better? Because repeated ANOVA, we only look, is there a change between the different time measurements? Here we can define the value on time. Of course, it could be that here is baseline. From baseline to there, it's 2 months instead of 1. But from there to there, it's 1 month. Then we could define this is 0, this is 2, and so on. So we adjust these values to exactly fit the actual time points. Okay. If we want to repeat a mixed ANOVA, when would we use a mixed ANOVA, for example? We don't only have time, we also have group. For instance, experimental group, treatment group, control with control group. Could we have that in our model? Yes, we could add. Let's say that's a group. 0 for control group, 1 for treatment group. So we say that if you receive treatment or not, let's assume it has an effect on the intercept. Let's assume it has an effect on the slope. And here we don't specify those effects. We calculate them. What do we want to see? What do we want to see about that effect? The effect of treatment group on intercept. What would we prefer? No effect, no significant effect. Because we want the treatment and control group to be equal at the beginning of the period. But we would like to see an effect from treatment group on slope. If it's positive, let's say 0 for control group, 1 for treatment group, and this effect is positive, it says, what is the difference in the slope between the control group and the treatment group? If it's positive, the slope is more positive for the treatment group than for the control group. Negative, the slope is more negative. Positive, the increase, if it's positive could be bigger increase or a smaller decrease. Both would be a positive effect. Now we have a mixed ANOVA. And the interaction effect, time group interaction, is equivalent with this parameter here. The effect of group on the slope. So of course we have not become experts on this, but I know you can analyze longitudinal data with structural equation modeling also. And one of the nice things that you can't do with a mixed ANOVA is, of course, these might not be manifest variables, the outcome. It might be, I don't know, Beck depression inventory with 40 items measured at 4 time points. Then you might have a latent outcome variable here with 40 indicators. The same latent variable with 40 indicators, and so on. But in that case, you have to do some more with it. You have to define that your factor matrix is equal on each time point. But it's not very difficult to do that. But you can have a latent outcome variables here, which you can't in ANOVA. Okay. Well, that's all I had. So let's have lunch.